Okay, now in this video, we're going to look at the number e. That's right, the number e. Okay, so we've been talking about exponential functions of the order y equals a to the x, and we did state that the value of a can be any positive value, rational or irrational. So we did look at and consider y equals pi to the x, and here we see its graph, much like any other exponential function, 2 to the x, 3 to the x. Okay, we look at radical 2 to the x, and here comes its graph. And again, radical 2, approximately 1.41. You can easily ask Desmos, your calculator, to graph those. It wouldn't struggle at all. It'd be the same kind of graph as 2 to the x or 3 to the x or any other exponential function. Okay. Radical 3 to the x, again, okay, approximately 1.71 to the x, and has the same behavior, ever increasing, intercept of 1, because anything that is 0 power is 1. You know, what the only thing that's going to change looking at these is the rate at which the graph is climbing. Okay, the larger the base, the quicker it's going to climb. And now we look at this e to the x graph, and go ahead and let your calculator look at it, and you're going to ask, well, what is e? What is the number e? Okay, well, the number e is what we call the Euler number, and it came about by its inventor, if you will, Leonhard Euler. Okay, somewhere in the 16th, 17th, 15th, or 16th or 17th century, I guess. E is an irrational number, like pi or any other root 2, root 3, any other irrational number, okay, which is approximated, like pi is approximated, at 2.7181. And again, being irrational, there's no end in sight to the string of digits, no pattern in sight. And there's this graph. I mean, you look at that alongside of maybe 3 to the x or 2 to the x, and you're going to see, well, it's sandwiched right in between the two of them, okay? So, but I know inquiring minds want to know, and we will look at that. But at first, we look at the features of the graph and find that it's really no different than any other exponential function graph, okay? And as summarized here, it's steadily increasing, having the negative x-axis as its asymptote, and a y-intercept of 1. So, like any other exponential function, it is very uncharacteristic in terms of its shape and, intercept and an asymptote. Okay, but let's get a feeling for what the number e is. Okay, would you say that e is less than 1/2? Well, no, e is 271, which is not less than 1/2. Would you say radical e is less than 1? Well, again, you don't need to know what it is, but the only values, roots of anything less than 1 would have to be fractional values, so that's not the case, okay? Is e squared less than 9? Yeah, well, 9 is 3 squared, and e is 271, so there you go, okay? Is e to the 0 1? Yes, anything to the 0 is 1. And that's why its features are so much like those of any other exponential function. The y-intercept is 1. Okay. Is e to the negative 1 less than 0? Well, no. E to the negative 1 is 1 over e, which is like 1 over a third. Okay. The negative exponent does not make it negative. Is e greater than 5/2? Yeah, it's like 271. Okay. But, okay, how did they come about with this number e? Well, take a look at this function. Okay, e is the horizontal asymptote of this function. And this is, again, something we'll invite you to do on your calculator. We're going to do it here. You can explore it here and, confirm it for yourself with your calculator. You take the function 1 plus 1 over x to the x. and you push this value of x out larger and larger and larger, which means you're looking for where it goes as x approaches infinity. So we're going to let our calculator explain that a little bit. So, okay, but at first we're just going to put in some small values. We're going to start out 1, 2, 3 and see what happens. So for 1, we get 1 plus 1 over 1, which is 2 to the first, which is 2. For 2, we get 1 plus 1 half, which is 3 halves, squared, which is 9 fourths, which is decimally equivalent to 225, okay? For 3, we get 1 and 1/3 to the third, that's 4/3 to the third, 64 27ths, which is 2.37. So you can see that this is growing, but okay, you could be interested in to see, well, does it have, what happens when we get out very large? And of course, we don't want to resort to all that hand calculation, so we're going to let our calculator, okay, do that work for us. So here we go, okay? So we're keying in this function, very simply, all right? And then we're going to go to our table, and we're going to say, well, okay, let's get a table and set it to the ASK mode so we can put in some values, and then we're going to put in increasingly larger values. We put in 1, 2, 3, and we saw where that went. So we'll put in larger. We'll put in, 10, 100, 1,000, 10,000. So as you can see, okay, putting in 10, you get 2.59. Again, we were coming up from 2 with evaluating this at 1. So now at 5, we come 243, 10, 2.59, so on and so forth. Look at what we get up to at 1,000, 2.7169. 10,000, 2.718. Now that's not E, but you can see it's heading for it. It's heading for it. So that's what's happening. That is becoming the end behavior of the function, or this is the end behavior of this function, or the asymptote for this function is the number E. Okay, so we can officially say that definition of the number E. The definition is the end behavior of this function, but the end behavior in calculus, as I've alluded to, is simply the the limit as x approaches infinity. So that is exactly what E is. E is the limit as x goes to infinity of the function 1 plus 1 over x to the number x. Now let's get just gonna make sure we got a handle on what E is with some of these lines of questioning. So we got the graph, we got the function y equals e to the x, again 271 to the x. We want to ask, is it always increasing? Yes, it's an exponential function whose a value is greater than 1. It's always increasing. So it's not always decreasing. Turning points, no. Turning points are inherent in polynomial functions, okay? Where we have the roller coaster rides of sort. So it's not happening. The function is 1 to 1. Yeah, well, it is 1 to 1 because all the exponential functions are 1 to 1, which is going to imply, of course, that it has an inverse, okay? The function contains an asymptote. Yeah, it's an exponential function. Certainly not a polynomial function. And the domain is everything. And the real numbers are not everything. And the real numbers, the range is just the positives, okay? You should just envision that y equals negative e to the x is just a flip across the x-axis. So then you should be able to match the properties that has. This we should see as a flip across the x-axis, across the y-axis, which of course forces it to become decreasing, but still preserves its one-to-one nature and still preserves its domain and its range, okay? This would be an interesting graph. I'm going to let you think about that one. And, essentially, you get this, e to the first is 271, e to the, put in negative 1, you get 271. And so you might be curious about that function. And I'd suggest that you take a look at it. If you can't figure it out on your own, ask your calculator. Well, what's this? This is a line. don't get faked out. It's just using a number, but an irrational number. Right? So the E is the y-intercept, right? So it's just a line with y-intercept, and of course you know what the lines are all about over there. Yeah, this is just a parabola, and the low point is at E. Okay, that's the negative b over 2a is right there on the y-axis at E, and this is a rational function. Okay, don't I mean, it behaves the same as well, excuse me, it's not a rational function at all. It's just a line with slope of 1/8. I like that, 1/8. Here's my rational function. I knew I had one in there. 1 over x, or same as saying e over x, okay? So, it's going to have that same kind of thing as 1 over x is just going to, the rate at which it approaches the asymptote is going to be a little quicker. So there you are. That's everything that is dealing with the number e.